We can all do an update. How's research going for everybody?
It's awesome.
Well, that's good. Hopefully that lasts.
Not this class.
Of course, not this class. Obviously, we're talking about other classes. Not as good as 232 though.
What's that?
232 is definitely that's the peak. It only goes downhill from there. How about for you?
Oh. Figure it out.
Find a groove. Yeah. Blake? In sim, in real? It is? Nice. Are you using the SAPG thing or just PPO is enough?
I'm using that.
Yeah.
Yeah, I'm using like what I think is a better version. So I have looked at that and I realized that they do a bunch of, well, everyone does a bunch of hacks. And I added my own hacks.
Yeah.
That's,
Blake reset.
the being that way I can say it like
Blake's large aggregation kinetic energy method. I don't know. All right, yeah, Blake's method will be the subject of next lecture. But this time we're going to talk about optimal or even optimization-based control. I think that this is the class missing from the current CDS offerings at Caltech that is most sorely missed. It can be taught in a variety of ways, from very theoretical to very practical, and I think all of those have a lot of merit. Today's is going to focus primarily on practical. I'll write things down that have math in them, but it's definitely going to be more of a practically focused lecture, I think, because there hasn't been a lot of practical focus in the curriculum so far. So we'll do an overview of the principle of optimality and HJB that I already kind of discussed in the 233 class on optimal control, but we'll sort of do it again. And then that will be kind of the only thing we really talk about from a theoretical perspective. We'll then go into trajectory optimization and transcription methods, which transcription methods, there's really only one that you need to know, but I think there are some that are historically relevant and are maybe good ones not to know because you're going to use them, but knowing why they are not in use anymore might be helpful. And then we'll talk about some solvers and ways to approach solving those problems, and then implementation details. And kind of the moral of the story of today is that being a practitioner of optimal control is all about admitting to yourself that the problem you're trying to solve is just way too hard, and like sacrificing all of your principles to slowly degrade what you're doing until it like doesn't make any sense, but probably works. So we'll start with this like bright golden beautiful piece of optimal control theory with HJB. It'll be like the world is awesome. We can write down any problem we want, and the solution has all the properties we could ever need. And it's like, okay, well, we can't solve that, so we're going to do trajectory optimization instead. It's like, okay, well, we can't really do the trajectory optimization problem, so we're going to transcribe it into an NLP, and then we'll be good. But it's actually not like a convex program, so we can't solve the NLP. So we're going to have to come up with some solvers and like relax that a bit. But even our relaxations, we can't run in real time. So it's kind of a decimation of optimal control is maybe how I would title this lecture most aggressively. Any comments or questions or viewpoints before we start?
Yeah, it's kind of
Yeah, all of my lectures are depressing, but I think the true merit is learning that they're not depressing. You know, there's nothing wrong with this. This is like something that is just because something is necessary and you want it to be different doesn't make it depressing, right? There's still a lot of beautiful, great things we can do with all of this. Um, but it is important to be aware of that like process of degradation. Because if you sit at only one of these levels and like don't know either the way up or the way down, you do not have a whole picture of like how this thing works. And so when you'll get some PDE theorist who comes up to you and like is telling you all these like great properties of the Hamilton-Jacobi reachability PDE, and they're like, why do you even use barrier functions? Reachability is way better. You can be like, okay, yeah, but for my 6-dimensional system, it would take me 18 million hours to compute the solution to your reachability problem. So like, I'm going to use the barrier function instead, right? Um, so being aware of the trade-offs here, I think, is really important. Are we suitably undepressed? Good. Okay. All right. Optimal control. Okay. Because this is not a super prepped lecture, there's going to be a lot of back and forth between like continuous time, discrete time, all sorts of different notations and whatnot. I'm going to just write one on the board to kind of get us started, and then I will assume that you are capable of extrapolating between like continuous and discrete time variance and all these other things, rather than spend a bunch of time to get the notation all correct at the start. Okay, so an optimal control problem is always going to have a set of dynamics, which we can express either as a differential equation or as a difference equation if this was an xk plus 1 and an xk uk for discrete dynamics. And we are going to be trying to effectively minimize some cost functional. So cost functional is something that is mapping us from an initial condition and a input trajectory. So this is like u of t, where t is defined over 0 to infinity. And the cost functional that we're going to consider is the integral of a stage cost over some infinite horizon. The finite horizon problem is analogous, but the value function becomes dependent on time, and I don't want to carry the time argument all around. And I don't think that the math changes too much to the level of understanding that I'm aiming for today. So we're going to do the infinite time one just so that the value function doesn't depend on time. And then we also will allow ourselves to have a bunch of constraints. And you'll note that we're going to keep these very general. When we talked about this in the lecture during the year, we like made some assumptions about the form of this stage cost, and maybe we made some assumptions about convexity or things of these constraints. Not going to worry about all that right now. We'll be more general. But in general, the state X has to lie within some set and the state U has to lie within some set. And then again, we could make this discrete if we wanted to by changing things out for discrete dynamics. And then also the integral would become a summation, and that would be enough. And then our last piece is that we have the value function, which is obtained by minimizing over trajectories u the value of the cost functional. Okay, so the value function is telling us that if we're in a state X and we apply the optimal control, we will incur this amount of cost over the, in this case, infinite horizon while executing the optimal control. The really nice thing about optimal control problems is that writing this problem down is very constructive, right? When I have a problem like the linear quadratic regulator problem, it is quite natural for me to say, my goal is to drive the system to the origin. A very natural way to express that goal mathematically is the integrated distance from the origin. We put that into a stage cost, we get some dynamics, we've constructed a optimization problem that says exactly what we want to do. And we talked about this a bit during the optimal or the controls course, nonlinear control. But construction is a really hard thing to do in a lot of control applications, right? And so the ability for us to be able to write a problem sort of directly into a form where we can analyze it is an advantage. We don't have to think about, oh, is this the right choice of outputs? Or like, is our system relative degree? There's not as many assumptions or things that we need to check. It's like, look, optimization problem, get ready to go. And this is sort of powerful from a practical perspective, but it hides a lot of nastiness from a technical perspective. We can write this down, and then what I'm about to do is I'm just going to move on. And I'm not going to talk about all of the many, many sort of technical conditions that we need all of these things to satisfy in order for the value function to be smooth or the value function to be well-defined and all of this. So if you're breaking into the theory of optimal control, you need to spend a lot of time thinking about these sorts of technical conditions and realizing that you're paying a price in terms of edge cases when you write down this sort of very general optimal control problem and feel good about yourself. Okay. Any questions on the statement of the optimal control problem? No? Okay. Okay. A lot of our analysis of the optimal control problem, especially sort of as it relates to the derivation of HJB, are inspired by, governed by this fairly intuitive, hopefully, mathematical principle called the principle of optimality. And I'm going to start by demonstrating it just with a sort of pictorial example, and then we'll talk about what it means more mathematically. But if I want to think about the shortest path that I can draw in the plane joining the points A and B, I am going to just assert that this is the path. And we will say that if it is not the path, that's because I didn't draw the problem correctly and not because it's not actually not the path. So I have drawn the optimal shortest path connecting the points A and B. And the question that we want to think about when it comes to the principle of optimality is if we take a point on the path. So I'm going to say that R of AB is the path joining A to B. And then we're going to say that this point C is a point that's on the path. What the principle of optimality says is it says that the path or the component of the path joining C to B is also optimal. Okay, so if we're talking about shortest paths, the idea is that if we go along the shortest path from A to B, and then we think, okay, well, what is the shortest path from C to B? Well, it has to be the remainder of the optimal path from A to B. And I won't do the proof sort of rigorously mathematically, but for contradiction, we could just assume that there was some other path that was shorter, right? So I'm going to take for assumption that the red path is actually shorter than the blue path. Well, this means that the original path from A to B couldn't have been optimal, because if I just took the initial path and then the red path, that would have shorter overall length when getting from A to B. So principle of optimality says, sort of colloquially, that any subpath of an optimal path is also optimal. Okay, and we can write that sort of mathematically, or a consequence of this statement um, can be sort of written in terms of the value function. Okay, so here we're saying that the value function at some state x of t is equal to the cost that you accumulate during traversing a subcomponent of that path with the value function's cost to go from the place that you get to. So if we apply that to this image, right, and we just say that v is equal to the length of the path, what this is saying is this is the length of the entire path from A to B, and the length from A to B has to be equal to the shortest path, so the optimal path from A to C, plus the sort of remainder of the optimal trajectory, which is the shortest path from C to B. Okay, are we clear on the sketch of the statement of the principle of optimality and then how it relates to this sort of composable statement of the value function? There's two assumptions that go into this being true that we're sort of glossing over. They're satisfied by these dynamics, but just to be sort of clear about them. One is that the cost is separable, right? So quite literally what this is saying is that the cost over any trajectory is the sum of the cost over components of the trajectory. And it's explicitly a sum, right? And not some other kind of mathematical operation. So the cost needs to be separable, and the integral is kind of this very nicely separable object in continuous time. And then the other assumption is that the dynamics are Markovian. So Markovian means that my next state depends only on my current state and my current input. And if the dynamics are non-Markovian, meaning they depend on the past, then it won't typically be possible to write the value function as only a value of your current state. So if you have a non-Markovian dynamical process, then all of this gets a lot more complicated and v won't depend only on x. You can get around that if you have a finite history by just stacking the history into the big state vector, and then it all looks like this again. Okay, but a couple of technical comments. All right. So the only sort of piece of real math that we're going to do today, and real is even maybe a stretch, is we're going to, again, go from the principle of optimality to the HJB equation through sort of one variational analysis on that equation. And to do that, we are going to look at this exact equation, and we're going to say that the difference between t and t is going to be small. So I'm going to consider a small amount of time h for which we're going to look at this solution. And so we're then going to basically just expand linear approximations of relevant quantities there. So we'll start with x of t plus h. And again, taking sort of a Taylor expansion here. We have that getting h units of time later is the initial condition plus h times the linearization of the trajectory at the point, and then our error is on the order of h squared. And then we will also look at v of x of t plus h is equal to v of x of t plus dv dv dx times, and then we have here so again, we're viewing this in terms of a first order perturbation. And this will end up being effectively a chain rule where we have the gradient of the value function v, and then the h f of x is again sort of a first order approximation of the dynamics, where this term should look a lot like our dv f of x v dot term that comes up a lot in the Lyapunov analysis. And then the last term that we need to expand is the integral. Where this one will be sort of exactly equal to h L of xu O of h squared. And effectively now we can just plug each of these linear approximations into the principle of optimality. And this will become some big long mess. So this was plugging in for the integral. And then next we have v of x of t. And we can cancel the v of x on both sides. And again, we have the sort of remaining h squared error term. We'll divide through by h to get ourselves something which is on the order of just O of h for the error, and then we can take the limit as h approaches 0, and we will end ourselves with the HJB equation. Okay, so we did that derivation in class, so we went through it a little bit quickly here. I really wanted to sort of first introduce the principle of optimality, and then again walk through this derivation that ends up with the HJB equation. And mostly so that we can now talk about the philosophy of why this equation is powerful and why it's useless. Any questions on the bit of math? Okay, so first, a statement on why this is powerful. We have, if we can find a smooth function v that satisfies the HJB equation, then this sort of constructively gives us a controller, right? And often it may even be, if not convex, this is an unconstrained nonlinear program. So this may be like quite easy to solve in practice. So if we have access to the function v, u is just the argument of this expression, which is something that is definitely calculatable. And that's a feedback controller, right? Like we just plug in the value for x and then we get the value for u, and that controller is optimal with respect to this control objective. So in a sentiment which might feel reminiscent of Lyapunov functions, if we have the function v, then we have a controller that is going to give us all of the properties that we want from the optimal control problem. That is kind of the shining promise of optimal control. It says that the value function is the only thing that you need in order to make great decisions over sort of arbitrarily long time horizons. And the downside of this is that not only is this function v hard to find, but it typically doesn't even exist in general, right? The caveat here was that v needed to be smooth or differentiable. There's a dv dx here. But when you write down optimal control problems that look like this, typically they are going to lead to continuous but actually not differentiable functions v for the value function. And so you do a bunch of extra work to come up with viscosity solutions where you can approximate the solution to the optimal control problem with a smooth v, and et cetera. And this leads you to basically the class of like numerical solutions. So how do we use this? The first option is there are some cases where we get problems where we can solve this analytically. Who can name the canonical HJB problem we solve analytically all the time? Somebody's got it. You don't need a hint. There's only one. The one optimal control problem that we always solve. It looks a lot like that. But it has a specific assumption on the kind of dynamics and the kind of cost. Thank you. Okay, so in the specific subcase where we have a quadratic cost and linear dynamics, then this equation becomes exactly solvable, and we can do it all analytically. So this is sort of our best case scenario. But as soon as we leave linear quadratic regulator land, that pretty much never happens. Which leaves us in numerical land. Our Berkeley student who left in the beginning of this lecture works with Karen Liu a bit, and there are people who do a ton of work on numerically solving equations that look like this. There's not only, of course, the HJB equation, but there's also reachability equations, and there's a lot of different families and kinds of PDEs that solve control-related problems that look like this and have similar computational complexities. And of course, the problem is that this PDE is not easy to solve, right? So the primary issue here is going to be one of dimensionality. So if we exceed, I mean, we're talking exceeding 4 dimensions we no longer are going to be able to solve even a numerical approximation to the value function. So the PDE solutions just really don't scale well to higher dimensional PDEs. And so the curse of dimensionality bites really hard. If you're trying to do a control problem that's higher than 4 dimensions, you're like out of tools. The PDE is just going to be intractable. There's not going to be a lot that you can do with it. And this is why the HJB equation by itself does not underlie almost any of sort of practical optimal control in autonomous systems, at least for autonomous systems that are higher than 4 dimensions. Now, it's worth noting, right, that we do have a lot of methods, and we'll talk about some of these methods later in like layered control, et cetera, where we can take big, hard problems, separate them into potentially low-dimensional problems, things like navigation or kinematic collision avoidance, which may be low-dimensional. You might be able to do some of these methods on those low-dimensional systems, and then you have different control methods to handle the really high-dimensional part, right? So if I have a drone, I might be able to do reach-avoid calculations on a reduced order model of the drone, and then I have a drone tracking controller, which we know how to do really, really well, that handles the low-level control and makes sure that that problem stays in its lower dimensional state. Okay, questions on the basic introduction to optimal control? Okay. So the really nice thing about this is that it gives us a controller everywhere, right? The statement is that for any x, I plug in an x and I can get out a controller u. The sort of first relaxation that we will often make is to, instead of trying to query the optimal solution sort of at all points in space, we will query the optimal solution only at one point in space. So instead of this being a problem that we're trying to solve everywhere, we will switch it up and we will set a fixed initial condition x0, which we typically give a different name, which is trajectory optimization. So we can't solve it everywhere. And we will fix the initial condition. Once we've fixed the initial condition, basically, we don't need to think about the initial condition here anymore. And then we will get another constraint, basically, which fixes the initial condition to the problem. So before, the cost functional was a function of depended sort of on where we started in space. And now we're saying, okay, I actually know where I start in space. I have an initial condition. This is now what we would call a trajectory optimization problem rather than an optimal control problem. And trajectory optimization will also typically tend to be finite horizon since we're getting more towards practical methods. It's really hard for me to represent an infinite horizon trajectory numerically at all. Okay. So the trajectory optimization problem is still looking for a control sequence that minimizes the cost functional that we've written down. The main difference here is that now we have the initial condition constraint. And so we've swapped from trying to solve the problem everywhere to solving it from one initial condition. And then the idea is that this is the difference between a feedback controller and a feed forward. Right, so U of t that we get out is just going to be a feed forward control, right? That is to say that if we applied it you could apply U just as a function of time, but that is explicitly not a feedback controller, right? Solving the trajectory optimization problem does not give us a feedback controller. It only gives us a feed-forward control. And so we will have to be clever about how to generate feedback controllers from the solutions to trajectory optimization problems. Because in general, just applying the feed-forward control is not enough to accomplish our control objective. You'll have error, the error will compound, and you'll sort of be far away from where you thought you were going to be when you started. Okay. Most of that we had sort of talked about before, so I just want to check in any questions on anything we've discussed so far. I went through it a little bit quickly, but I also thought that it was maybe something that everybody in the room had seen before, so didn't need to dwell. Okay, so we talked about the principle of optimality. HJB equation is too difficult to solve, so we change our problem statement to a trajectory optimization problem. Okay, clear. Well, sort of right away, we're faced with the next issue, which is that this problem is also one that we can't really solve, right? We got over there and we had a PDE, and the PDE was difficult. This one, we no longer have to go to the HJB equation and get the PDE. Like this is the problem that we're trying to solve, even if we're trying to solve it numerically. But there's no optimization solvers out there that are going to like take in a differential equation, right? IPOpt doesn't have like a differential equation toolbox where I can just hand it an ODE and it will like continuously enforce the ODE over the horizon that I'm trying to optimize. So the first thing that I need to do is I need to come up with a way to take a problem that looks like this and interface it with a numerical solver. And coming up with that interface is the process of transcribing the trajectory optimization problem. So transcription is we want to interface the trajopt problem with an NLP solver. NLP standing for nonlinear program. We'll talk about solvers in a bit, but first I just wanted to go through the transcription approaches. Okay, so single shooting and multiple shooting both were popular back when computers were tiny. So they're mentioned primarily for historical relevance. And then the method that is going to be the primary choice today is called direct collocation. Okay, are people familiar with these terms? I'm going to go over them, but okay, I just wanted to see that hopefully we're starting to hit on things that are new. Okay, so to clarify sort of exactly what I mean, a NLP solver is going to take in a problem that looks like this. This is pretty general, but specifically these functions f and g needs to be functions I can write down sort of analytically like in a programming language, right? And F needs to be a scalar objective. G can be a bunch of things stacked, but it needs to be finitely many things stacked, right? So a ordinary differential equation is not like a finite number of equations that I can sort of stack here, right? Like enforcing the ODE would be kind of forcing an infinite number of constraints. So the work that we're going to do is basically how do we go from that problem and put it into a form where it looks like this. We need to define the objective function and define the constraint functions. The first thing that you need to do, sort of regardless of which transcription method, is to discretize the dynamics. And I'm not going to sort of belabor this point too much, but the idea is that we're going to do something to take the differential equation and change it into something that looks like this. Typically, we're going to do this via Euler integration, or maybe RK4 integration, but you're going to just come up with a numerical integration scheme where you simply integrate the nonlinear dynamics term, and the result of the integration scheme will be a discrete nonlinear dynamical system. Yeah. Say it again. Thanks. Yeah, we're going to enforce a fixed point on our dynamics. The constraint is, yeah, invariance under the action U. Okay, so once we have discretized our dynamics, we still actually have several different approaches that we can take when describing what the NLP looks like. And I'll make one more note. I'll even just change this so that it's more clear. One thing that we get to decide is what the decision variables are. So the decision variables is the set of variables that the optimizer is going to consider as things that it can change. And this is actually one of the main choices that we get to make. So in single shooting, the decision variables are just the inputs, U. So inputs only. And what this does is it makes the constraints really, really annoying to write down. So we're just going to kind of use a bunch of dot, dot, dots. But if we think about the dynamics constraints that we need to enforce, right? Well, the first dynamics constraint, looks like this. We say x1 is equal to f of x0, u0. The next one is going to be x2 equals f of x0, x1, u1. But I could equivalently write this as f of, and then instead of x1, I can plug in f of x0, u0. So what I can do now is anywhere that an x2 shows up in my optimization problem, instead of writing an x2, I can write an f of x0, u0, u1, right? And x0 is not a decision variable, right? That is a value that is fixed. The initial condition is fixed when I'm generating this control problem. u0 and u1 are decision variables. They're the controls. But what ends up happening is basically everywhere that a variable x shows up in that optimization problem, instead of writing x, I can write a sufficiently long iterated list of f's and all of the relevant u's. So specifically, the function f of z which the integral is going to become a summation when we discretize. F of z is going to be equal to L of x0 u0, where again, this is not a decision variable, right? So yeah. You never do. What is what does it mean to discretize fine enough? So, okay, if we want to think about guarantees in something like a trajectory optimization pipeline, we need to think about what we're trying to guarantee, because any discretization will not be dynamically feasible. The solution will not be exact. So there's a statement about like, what are you trying to right. And so we need to be mathematically precise about what any of those things mean.
I guess I forget what it's called. We talked about doing the like you wait to apply the control input, and then you treat that kind of step as like an X property system.
Yeah, so when we were doing event triggered control, we thought about this like deviation. I think these are pretty unrelated. Coming up with a time step is a question of like, what are you going to do with the solution when you have it, right? So there's a bunch of different things I could do. I could try to track the solution. And if I'm trying to track the solution, then the question is like the solution is how dynamically feasible is it? How close does it go to the constraints? These are all things that are going to be functions of the discretization. If you're trying to actually make proofs of these things, then you can Lipschitz bound the error from the solver, basically, and you can come up with these exponentially exploding tubes that come off everything. And then you can back out some, I mean, like we did in the event-triggered control lecture, you can back out a bound that will say how tight do I need to make my discretization for my trajectory to be this close to dynamically feasible, such that when I track it, I incur at most this much error. And then you do that, and then time discretization will be like 1e to the minus 12. So you'll be like, ah, shoot. But this is the approach that you would take if you wanted to guarantee something. But I would say just the question of like, how do I guarantee the solution doesn't really parse? The solution will not be correct. It will be an approximation. And you need to think about like what it is that you're trying to guarantee when you go to compute what sort of step size that you actually need. Practically, this solution or this problem will be governed by, very practical things like does it work? And the idea being that the coarser discretization you can get away with, the longer of a horizon you can consider with less decision variables, right? And as we'll talk about when we get to the implementation details, there's this very complicated relationship between how fast you might need to recompute solutions to the optimization problem and how fast you can actually compute solutions to the optimization problem. And so typically you will need the solutions fast, but you can't compute them fast. And then there'll be this weird interplay where the finer the discretization, the better the solution, and the slower you could compute it. Like because the solution is high quality, you actually don't need it as fast. But you've made the problem bigger and you've made it slower to compute because you discretized all fine. And then on the other end, it's like if I don't discretize very finely, I take big jumps, I can compute the solution faster, but I need it faster because each solution is actually garbage. And so then there's a really sort of complicated engineering problem of how to hit a sweet spot between those two where you can compute things fast enough, but they're of high enough quality. And we'll talk about that in a bit. Yeah. Other discretization related questions? Okay, going back to the objective function. The objective function is a sum of these terms, but the idea is that instead of putting an x1, I'm going to put an f of x0, u0, and then a u1. And then I'm going to put a dot, dot, dot. So again, this is now going to be a really long sum, and the terms of the sum are going to include increasingly many iterative applications of the dynamics F. And then G of Z, in this case, we actually won't have any dynamics constraints because we're sort of removing all of the successive states, x1, x2, etc., and we're enforcing them explicitly through the structure of the problem. So we don't have to worry about dynamics constraints, which is nice, which means the only thing that we need to worry about is basically we'll need to enforce the input constraints, right, that U lies in the remaining set. And then we will also need to enforce things like f of x0, u0 lies within x. So if we have state constraints, again, instead of saying x1 lies in x, we will say if we start at the initial condition and roll out the dynamics to x1, that sort of implicit state has to lie within the state x. And then, we'll also get something that looks like f of okay, so our nonlinear program is governed by the objective function and the constraints. And we're basically going to rewrite these, eliminating all of the intermediate variables x, so that the decision variables are only the inputs, u. Is the single shooting approach sort of generally clear? Do we have ideas about, like everything, this is a trade-off, what is good and what is bad about the single shooting method? Start with good. Anybody have a positive aspect of single shooting? We can just guess. I know we haven't all implemented single shooting methods. Hopefully none of us have implemented single shooting methods. Any ideas? No. Yeah, speed, things like, yeah, how much is the implementer or the solver, like the numerical solver we're going to use, hate or like this problem? There are, yeah, okay, right. So and that is a negative. Yeah, okay. So one of the negative things is this recursive application of f. When we take f and we apply f over and over and over, if f is nonlinear, that nonlinearity compounds, right? So if we start with a function that's like loosely nonlinear and we apply it to itself like 20 times, that resulting function is going to be very nonlinear, right? So when we try to go differentiate through this thing, the derivatives we're going to get are going to be a mess. They're going to change really, really rapidly, and they're going to be really large. And what that ends up looking like is really big sensitivities in the solver. If you think about if this is like the input, right? And say I take some input to my system, and then I take that input, I integrate it, and I get like an output, or I get the state x. If I change an input like way back at the back, right? So let's say that I take this input and I like jump it up to here. What that does can have massive impacts on where the system ends up evolving in the state space, because that input u impacts like the entire rest of the iterative dynamics, right? U0 shows up in every single term in the cost, and it shows up in every single term in the constraint. So if I need to move U0, it impacts literally everything that's happening in the optimization problem at once. Like every single cost and every single constraint is getting changed at once. So how am I supposed to figure out like good directions to move U0? There's like no way. It's going to be way too difficult, because if I move it up, my trajectory is going to just look completely different because I changed it and it was like at the root. So these iterative applications of the dynamics are going to make the problem really, really sensitive. And This is actually even true regardless of whether the problem is linear or nonlinear, because if you think about iterated linear dynamics, what we're getting is we're getting that A matrix to higher and higher powers. So if A has eigenvalues that are unstable, right? Like if A has an eigenvalue of 1, when I take A to the 20th power, now A is going to have eigenvalues that are like size 20 or higher. And so that means that unstable modes in my system get dramatically amplified by this like recursive iteration of the dynamics. And to that point, the sort of only successful application of single shooting methods is with systems which are already stable. So if I have a system where maybe say a linear system where the A matrix is already stable, now this iterative application of the dynamics doesn't blow up so much, right? In fact, it actually is contracting. So if we're in a space where the dynamics are already stable, then this might not be such a bad idea because the iterative application of f doesn't matter. But when the dynamics are unstable, the iterative application sort of blows up on us and it's going to make everything super, super sensitive. Okay, so that was the main con. Does anybody have a pro? There's sort of one main pro associated with single shooting. I like the way we're thinking. That's good. It is definitely constructive. Luckily, all of these transcription methods will be constructive. Okay, the one that I'm sort of fishing for here is that it has a very small number of decision variables. And maybe that's an unfair question for me to ask before I've shown the other methods which have more decision variables. But basically, when we do all these other ones, what we're going to do is we're going to add decision variables in order to reduce the amount of recursive application of f. So this optimization problem that we end up with is going to be small but complex. It's small because the number of decision variables is small, but it's complex for exactly this like recursive iteration of the dynamics f. Any questions on single shooting? I'm going to have an honorable mention here for something called ILQR. Single shooting you will never see. You would have seen it if we were like 20 years ago, but now I say a lot of like crazy things in here, but I am confident that you will not see vanilla single shooting as like a actual applied optimization scheme that somebody uses. There's a chance you'll run into iterative LQR. And iterative LQR uses this same scheme for a forward rollout, but then it uses LQR to do like a backwards pass on the optimization. I'm not going to go into the details, but ILQR is a like sort of another, it's not even really a transcription method as much as it is a solution method. It's a solution method that leverages this structure to go forward, and then it leverages a structure like LQR to go backward. And then you will sort of iterate on this a bunch of times where you roll out U and then do a backwards pass to update U, and then you roll out the new U and you kind of run back and forth. ILQR is a thing that people do, and it is one that's really only works well on systems that are already stable. So like we said, if the dynamics are stable, then you can kind of get away with this approach. If they're not, I wouldn't try it. Okay, multiple shooting. Okay, the difference with multiple shooting is we are going to introduce not points. I'm going to say, for instance, that we choose, say, x2, x5, x8. And now our decision variables, z, is going to be all the u's and then also some of the x's, like x2, x5, x8. Okay, and the idea is that now, if I want, say, an x1 to show up somewhere in my optimization problem, well, x1 is going to be f of x0, u0. If I want an x2, well, I actually have x2 as a decision variable, so I'm going to use x2 directly. If I want an x3, I'm going to apply f of x2, u2, right? So I apply the dynamics now not to x0, but to x2. And then similarly, if I wanted like an x9, I'm going to say f of x8, u8. So now if I have a trajectory of length 20, here I would end up with 20 iterative recursive applications of f anytime I wanted the last node like x20. Here, if I sort of like sub-discretize at, say, a length of 3, I never have more than 3 applications of my dynamics f in a row. And I'm not going to write these things out again. It's following the same way, right? So f of z will look the same, but instead of having a ton of iterative applications of f, we would only get up to 3, and then that applies sort of everywhere in the optimization problem. And then our trade-off is that we have added decision variables, right? So we have more decision variables than we did before. But we have reduced the complexity of the loss landscape. Right, so the idea is that now, before we said how if I change this, if I like perturb the initial control u, that perturbation impacts literally every other thing in the entire problem. Right? Every other component of my cost and all of my constraints depend on u. That is no longer the case in this multiple shooting method. Right? Now if I change u, and I only change u, the only thing that it will impact is anything, if I change u0, it will only impact things involving x1 and, actually as I've written it, only x1. And then if I change, say, u2, that will change x3 and x4. Yeah. Yeah, so we need to dive in. What do you mean by a greater ability to control the system and the dynamics? Yeah, so I guess, sorry, I needed to maybe finish my statement first. We've added decision variables. We have also added dynamics constraints. So over here, there were no dynamics constraints, right? The dynamics were sort of implicitly satisfied by the forward rollout. Here, the optimizer is actually going to get, as written, 3 additional constraints, a bunch of additional constraints that like constrain the dynamics to equality everywhere that we introduce one of these not points. So the flexibility you're talking about like definitely does not exist at the level of the system dynamics. It does, however, exist on the internals of the solver, right? The difference is here, you know, when I change this one variable, it impacts absolutely everything. In a multiple shooting approach, so again, we're going to have some trajectory u. And the multiple shooting approach will now have like a small sub-trajectory, and then it will have another small sub-trajectory, and then another small sub-trajectory, and it will kind of stitch these together. And the idea is that now you have equality constraints that say that these not points have to be equal. The flexibility that this buys you is while the solver is taking steps through the landscape, it will incur violation of those constraints, right? Like the constraints will basically be violated by small amounts as the solver converges to the solution. But that flexibility is kind of what you're saying. Like you get to sort of stick the point somewhere and say like, okay, it's good if I can get the trajectory to this part of the state space. I now need to like pull the tail up to satisfy the equality constraint. So, and that's what makes the loss landscape a lot better, right? Is because when I'm changing the inputs in this range, that's only moving this one segment of the trajectory. So my gradients are much better behaved, but I've paid the cost of additional decision variables and additional dynamics constraints. No, the U will, as stated, have like no smoothness properties. Also, we've discretized our system dynamics. So U is going to be like sample and hold anyway. So it won't be smooth either. For trajectory optimization, there is not a lot of reason for U to be smooth because it's not a feedback controller. U is like an open loop trajectory that I'm just going to roll out. There's no like spatial gradient of U. The reason we want controllers to be smooth, like when I say U equals K of X, I want that to be smooth because when I take perturbations of the controller K, I don't want my U to change a bunch. And that's true because of sensor noise, like uncertainty, perturbations to my dynamics. There are things that will perturb where I lie in the state space X. But this is not a feedback controller, right? Like even when I get perturbed in the state space X, all I have is U of t. And I'm going to know what time it is. So even when I get perturbed in the state space, I just apply the same input U. So the smoothness of the control signal U here matters a lot less than the smoothness does when we're thinking about feedback controller. But yeah, good question. Yeah. Yep. If you were doing optimization in 2004, you would have taken a lot of care. If you do optimization in 2020, whatever, you're going to do this. Okay, anybody want to guess what direct collocation is? The reason I propose it as a guess is because it is not impossible for you to derive it based on the trajectory that we've been going through the various methods so far. Okay, Blake doesn't know, so he can answer, yeah. Yes, so direct collocation is just all of my states are now also variables. And I enforce the dynamics constraint at every single node xk. I don't really want to erase stuff and write it down. So for the direct collocation, my decision variables are now both all of x and u. So I have even more variables and I have even more state constraints, or sorry, dynamics constraints. In fact, I can't have any more dynamics constraints. I'm using all of them. And same thing with the states. And so now, sort of on this picture, the direct collocation would now be, I only apply like one input at a time. And so like every single time that I apply an input, I jump. And so again, not to say this too many times, but the idea is the solver now has a lot of flexibility in terms of the state. It can, while it is searching for the solution, it can have errors at every single one of those little dynamics not points. That allows it to not be overly sensitive to all the inputs. Each input affects only one state, the next state. So your gradients are going to be much better behaved. When I'm thinking about the gradient of my control problem with respect to one of the U's, it's like really only affecting a couple of things, a handful of constraints and a handful of cost terms. So our problem has gotten way better behaved at the cost of we've doubled at least the number of states, and we have way more than doubled the number of constraints. Like the dynamics constraints are typically some of the harder constraints to solve. Correct. So what do I mean by is to solve the dynamics constraints? In the first case, there were no dynamics constraints. My solver would spit out a trajectory u. If I wanted to like get the trajectory that that u implied, I'd have to integrate it myself. Now the solver can spit out in the direct collocation, it will spit out both a trajectory u and a trajectory x. If the solver has done a good job, if I were to integrate u, I would get back x because it solved all those constraints to equality. But an actual nonlinear solver is not going to solve the constraints to equality. It'll solve them to 1e minus 4 maybe. But if it is like poorly conditioned, it might only solve them to 1e minus 2. Now, if I were to go integrate the solution u, it would actually be different than the trajectory x that gets spit back out. So when I say the solver has to solve the dynamics constraints, that means it has to enforce consistency between the x's and u's that it applies in accordance with each of these dynamics constraints. Okay, that's transcription methods. So the sort of philosophical statement I want to make here is I don't think you'll really see anything other than direct collocation today. But like even as short ago as when I was taking optimal control here, so we're talking 4 years ago or something, like they would have taught all of them, and maybe they would have had you implement all of them. But solvers have gotten better. The pressure to keep your number of decision variables has gone down, and I think the field is sort of at a consensus that direct collocation is better. Yeah. They look like this. Like x1 equals f of x0 u0. Mm-hmm. For the multiple shooting, I didn't really write a good example of this, but like in multiple shooting, I would have had x10 equals f of x8 u8 u9. So in multiple shooting, I would have gotten small chains of like 2 or 3. In direct collocation, I get no chains. It's always just one application of f, and it's at every single node x. But sort of the reason I didn't write this here is because this doesn't actually show up as a constraint, because x10 is not a decision variable. So this term would have showed up a bunch in the cost, but we don't actually see this term ever as a constraint. Whereas each of these terms we do see as like actual constraints showing up, basically. Or each of these terms will sort of get a constraint associated with them. Any other transcription method related questions? Oh, did I finish my philosophy? I don't know. I think really maybe one of the big takeaways here too is to understand this relationship between like sensitivity and transcription method. Like I think it is important to realize that your optimization problem is sensitive with respect to that first input. And collocation is like kind of hiding that sensitivity by breaking up how the constraints change things. But acknowledging that that sensitivity is there, I think is important to sort of understanding like how nonlinear solvers work. Um, yeah. Yeah, people have different names, slightly different naming conventions for these things. And in fact, what I'm presenting here is a pretty high level overview. Sometimes when people talk about transcription, they're also including this discretize the dynamics thing. So sometimes direct transcription, like if you go into the literature, sometimes you'll see things where the not points are actually like in the middle of the, what am I trying to say? If I have like u defined over this time interval, uh, sometimes the not point will actually be like located at the middle of the interval. So sometimes if people say direct transcription versus direct collocation, like the difference they'll be talking about is some weird not point thing. Um, I would say that to me, that is like a specific enough detail that it's like not even a piece of terminology. I would say those things are about equivalent. And then if somebody says that, you then need to figure out like what they mean specifically. In practice, I think that as I have written it down is like pretty much what people do practically these days. Yeah. So if your gun is Euler integration, then the single shooting method is you taking one shot and rolling out the entire trajectory as one integral. And then if your gun is Euler integration over here in multiple shooting, it's like you integrate for a little bit and then you integrate for a little bit, you integrate. So you're taking like these multiple integral steps with the not points in between. And then they could have called it like infinite shooting or something, but they didn't. Huh? Yeah. Yeah, semi-automatic transcription. Full semi-auto transcription. Yeah, Gatling transcription. Um, okay, transcription done. Solvers and approaches time. I know we're running out of time, so I'll try to go a little bit quicker, and then the implementation details can be very fast. Okay, we've written down an NLP, and it looks like that. It says min f of z subject to g of z less than or equal to 0, because we did transcription. The battle's not done, because now we have to solve that optimization problem. And to solve that optimization problem, since it's 2020, we get to just go pick from like the wealth of beautiful optimization solvers. We don't have to roll our own. Although it's also 2020, so we could just say, hey, Claude, roll me a direct collocation optimization solver. It could do that too. But there's a lot of solvers, and the solvers take different approaches to solving these problems. And I just wanted to mention a few of them. There's two main classes. Our first class of solvers is gradient-based. And when most people say NLP solver, they will mean a gradient-based solver. True. A gradient-based solver requires that your problem is differentiable. So if I want to use a gradient-based solver, f and g both need to be differentiable functions that I know. Can somebody think of a particular kind of dynamics that comes up in robotics often that is not differentiable? Contact. Awesome. So if my optimization problem involves contact and I want to use a gradient-based solver, I'm going to have to come up with some extra steps. So I'm going to not talk about those extra steps today, but Actually, why not? I'll talk about those extra steps. I'll just say some of the names. We have contact implicit optimization, where contact implicit optimization doesn't actually model contact as a binary, but it says that the table applies force to my finger depending on how far my finger is from the table. So a contact implicit solver is going to actually apply some force to my finger all the time, regardless of how far away I am. It will be like very close to zero when I'm far away. It will be some amount when I get close. And then as soon as I start to penetrate the table, it will go like really, really high, right? So contact implicit will basically say like the amount of force as a function of the distance, it will be really small and zero, and then it's going to like blow up really fast as I pass zero and start to penetrate the table. This is now differentiable. This is good. Other methods will use what are called complementarity constraints. And a complementarity constraint is something that looks like force times distance equals zero. So actually, this constraint is differentiable, but that's like a lie. I don't know. It's hiding some nastiness, basically. If you think about the gradient of this constraint, the gradient of the constraint will just be zero all the time, because like either you are not in contact, and so the distance is zero, and so the value of the constraint is zero. And when you're not in contact, like perturbation to the distance won't make you in contact, right? Like if I am here and I consider an epsilon perturbation, that's not putting me into contact. So even under the perturbation, I can't get force. And then same thing with the force. Like if I'm applying force, then my distance has to be zero. And if I perturb the amount of force I'm applying, well, it's still not zero. And so like my distance has to be zero. So it differentiates and it allows you to use it with differentiation or with gradient-based solvers, but the gradients are like useless. But is it clear how this product equaling zero like enforces contact? It says that either I'm getting no force and then my distance can be whatever, or if I am getting force, my distance has to be zero. And then similarly, if my distance is non-zero, then I can't be getting any force. Yeah. Oh, there's people who like POSA, there'll people who will do these complementarity conditions. Absolutely a valid solution approach. But specifically by useless, I mean like this gradient is useless to the optimizer. But the solution approach is definitely a valid one. And then there are like constraint-based formulations where instead of having the force sort of modeled explicitly, you might just like when we do locomotion, we typically don't model the constraint forces on the ground. We just say that when you're in contact, the foot can't move. And then that constraint sort of propagates through. Okay, that was a sidebar, really just because I knew you were going to be maybe interested in what the through contact stuff looked like. The real moral of the story is that we need gradients if we're going to use gradient-based optimization, and that you should be aware that there are things that break that assumption, like contact. Within gradient-based solvers, there are two families that I wanted to mention, which are interior point and sequential convexification. Okay, and I'm not going to go into too much detail here, but interior point methods say constraints are the problem. So an interior point solver makes the assertion that the reason that that NLP is hard to solve is because of the constraints. Okay, how do we solve an NLP with no constraints if it's differentiable? Yes, we just differentiate it and set it equal to 0, right? If it's convex, that works great. If it's not convex, we have to play some other tricks. But the idea being if the constraints aren't there, that problem's like a lot easier to solve. We're basically looking for the derivative equaling 0 somewhere. So interior point looks at that and it's like, man, those constraints are really getting in the way of my solution technique. So I'm going to take the constraints and get rid of them. And the way that we get rid of the constraints is, who took air names this class? There's only one word we need right now. Nope. It's his favorite word. His other favorite word. It's Sean's new favorite word. Blake knows it.
Yes.
What's the middle of CBF? Barrier. So where did the CBF idea come from? Barrier functions from interior point methods. So the CBF was inspired by the interior point method. But a barrier says, instead of a constraint, so we don't like constraints. Instead, I'm going to put a cost that looks like this. Minus log minus g of x is my cost. And if we plot minus log minus g of x, whoops, it looks like this. It has an asymptote at 0, and it blows up to infinity. And so the one problem with this is it's actually really bad if g of x is out here because it's like not defined. So interior point methods require feasible starts. Like you have to start with a point x that is feasible for all of the constraints. But then if you do, then basically this will say, look, as I get close to the constraint, I get sort of infinite cost. And you will solve it once, and you'll get an optimal solution where g is like well on the interior of the constraints. And then you'll make those barrier functions a little bit more aggressive. So they'll get like steeper and sort of closer to the boundary. And then as you do that over time, you'll sort of you'll relax the barriers and you'll let the solution kind of approach the constraint manifold over time. Again, I'm going high level here. If we can talk more about interior point methods if we want, but the idea that I want to get across is interior point says constraint is the problem. I take the constraint, I make it into a cost with a log barrier, and then I sort of like anneal that barrier until it becomes like the barrier is going to start like this and it's going to end as pretty much an L shape where it has 0 penalty and then jumps to infinity right on the boundary. So we kind of anneal the barrier until it looks more like a constraint. Okay, our other method, sequential convexification, says convexity is the problem. So sequential convexification looks at the problem and says, man, if this was a quadratic program, then we would be set. But it's not a quadratic program. It's like the constraints don't matter if they're linear and my objective function is quadratic. So all that the sequential convexification is going to do is it's going to linearize all the constraints. It's going to take quadratic approximations of the cost and then solve the resulting QP. Because if you've taken optimization, QP is like best case scenario. We can solve QPs really well. And the idea is that if you solve the QP, you've moved, you relinearize, re-quadraticize your objective, solve the QP again, you repeat this until you don't move anymore, right? So you'll run around solving these QPs until you get to a spot that's a fixed point, and that fixed point is a solution to the NLP. Yeah. This is the function I'm trying to optimize. I'm not going to draw constraints because it's complicated for a 1D problem, but let's say that my initial guess is here. And if I take a like quadratic approximation of my objective function, the quadratic approximation like looks like that. So I solve that. That's the solution to that like minimization problem. So that drops me down to a new point, and I take a new quadratic approximation of the function at that point, which now looks like this maybe. And so I solve that one, and that takes me to a new point. I take a new quadratic approximation, and I take the solution, and then you like dial in on the actual solution. And then, of course, this gets much more complicated when you take into account the constraints, right? But you could imagine, like, if I have a circular keep-in constraint, and like, maybe I'm right here right now, then what I'm going to do is I'm going to linearize that constraint, and then I'm going to solve the resulting quadratic program. That's going to spit me like here. This is actually really bad because I've left the constraint manifold. So we're going to do something special called a line search, where we draw a line back to our initial point, and we move backwards along the line until we get into the constraint set. Okay, we're back in the constraint set. That's our new point. We relinearize. We solve the QP again. We get out here. Now that was an issue, so we actually do the line search again, and you like go back into the set, and you keep doing that over and over until you converge. Make sense? Cool. Okay, so we got two gradient-based methods. One says the constraints are the problem, so we use log barriers to get rid of them. The other says convexity is the problem, so we take convex approximations of the program and solve those. Both of these are iterative approaches, where we will either iterate the log barrier or we will iterate the convexification until we get to convergence and the problem is solved at convergence. Good? Anybody have an idea for a optimization approach that is not gradient based? Yes, population-based methods are an example of what I'm going to posit, sort of. Yeah. Okay, population-based methods is perfect. I'm going to call them sampling-based methods. Okay, so there's sort of two varieties. That I'm going to sort of high level talk about. One is MPPI, stands for Model Predictive Path Integral, and I have no idea why, so you can go read the paper if you want to know why that's what it's called. All of the sampling-based optimizations will basically say, I am going to solve that optimization problem by taking a random guess for what z is. And then after my random guess, I will take a ton of random guesses, look at all the ones that I got, pick the best one using some metric, and then I will resample randomly around that like new guess at what the optima is. The real power is how we choose like which one to sort of resample around. MPPI will sample a bunch, and then it will compute the weight of the ith sample to be the x of the cost of minus cost over lambda. So basically, it will take each sample, it will compute a weight via this exponential of cost over lambda, and then it will take a weighted average of all the samples. So if we have some optimization landscape that looks, like this, and then we drew samples, say here, 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 and here, then this sample is going to get like a really big weight because it's really close to the optima. This one will get sort of a middling weight, and then these two will get low weights. Let me put my middling weight actually in the middle. You don't know if it's close to the optima, but you do know how much cost it has. And obviously lower costs will be closer to the optima. You don't know the absolute distance, but you know, actually, I should say, you don't even know how close they are in parameter space, but in cost space. And so when I say close, I mean close in cost space. Okay, and in MPPI methods, you're going to take a weighted combination of all of them, right? So the weighted combination is going to be like, I don't know, maybe it's going to be like dominated by this, have a little bit of this in it. So that's like here, and then equal parts of those two. So I'm going to say that the weighted combination is somewhere like that. And then what you do is you now will take new samples around that like new weighted combination. Like, help me out. I'm looking for cross entropy, CMAES, CM. I guess I have notes. Kind of forgot about those. CEM, cross entropy method. Okay, CEM sort of says instead of weighting all of them, I'm actually just going to evaluate the like top few. So in this example, I could actually just say whatever my best sample was, I'm just going to stay there. Instead of weighting all of my samples, I'm just going to go to the best one and then resample around that. And then, of course, there's tons of other methods that will do combos of these where you like weight the top K or you do other things. Okay. One of the main drawbacks of sampling-based methods is it is really, really hard to enforce constraints. How do I enforce a constraint in a sampling method, right? If I have like a dynamics constraint, for instance, that I wanted to enforce, that's like an equality constraint. I need to randomly sample on an equality constraint manifold. Zero measure set doesn't happen, right? So like a one-dimensional line in a two-dimensional space, I will never hit if I sample randomly. So all of these sampling-based methods only work on the single shooting transcription method. I can't apply a sampling-based method to something with the equality constraints that you get from direct collocation or multiple shooting. So I'm going to use a method that looks like single shooting. I can enforce input constraints because my inputs I'm sampling. So I can just say I only sample from like within the set of valid inputs. But if I have a state constraint, like stay inside the circle, it's really hard to enforce that state constraint because the really only tool that I have is rejection sampling. I can just say I forget about any samples that didn't land inside the state constraint. But if your state constraint is hard to hit, you'll just end up getting no samples. And so then you have nothing to optimize and your problem is really hard. If you're really, really, really smart, you might say, hey, what if I took all of those constraints, reformulated them as control barrier functions, filtered the sampled input such that it actually satisfied the CBF, and then we would satisfy the constraint. This is like a really good way around it. But in general, sampling-based methods struggle with constraints because you have to just like get lucky and sample things that are valid under the constraints. But the general approach is I take a bunch of samples, I have some way of picking where I want to sample about the next time, and then I like refit my distribution there, sample again, continue until I am satisfied. Questions on the solvers and approaches section? Yeah. I mean, that's the CBF enforces a constraint that is h of x is greater than or equal to 0. So I have a function that says g of z is less than or equal to 0. If g of z is a barrier function, then I am in fantastic shape. If it's not a barrier function, I need to convert g of z into a barrier function. using like any of the methods that we talked about from 233. Relative degree extension, higher order barriers, choosing a different constraint function, etc.
I've done based different
Yeah.
and read various. The way like I did it was that you almost project, so you project your sample point so that it satisfies the constraints.
Yep.
Is that like an option here?
Totally. It depends on what the constraint is. Like if I have a constraint that says, let's say it's a collision constraint, right? Like there's obstacles in the environment and I'm sampling inputs for a path such that they don't collide with the obstacle. If all I'm looking for is a geometric path, then yeah, I could just like project to the surface of the constraint. But if I'm like going to go apply the input, just projecting the point X back so that it doesn't collide, it doesn't help because the input like would have made me collide with the thing, right? Does that make sense? There's like a difference between whether I'm just trying to find a path or I'm trying to find like inputs that go along the path. So if I can't collide with this, and that's what my like optimized path does, the projection is not in the U space, right? The projection is in like the state X, right? And so that projection would like take this and put it here, and then maybe, I mean, it would actually like take, or that would be the only one that would get projected. So your system would still go like through the box. That's not really the point though. The point is that the solution is the set of U's. And projecting the state X doesn't tell me like what I need to do with U in order to make U safe. The thing that does do that is a control barrier function. When you get a U, control barrier function is literally a projection on U, right? It projects U from the set of all possible U's to the set of safe U's. So the control barrier function converts the state constraint into a input constraint and like applies the projection there. Any other questions on solvers and approaches? I'll do implementation really quick. Okay. Implementation details, I have two. One is for these solver-based methods. When you go to implement these, you can come up with good schemes for what to do with like parameters like lambda, or parameters that control your sampling. So if you're sampling from a Gaussian, something that makes sense to do is to like reduce the size of that Gaussian over time. So you're like coming into the optimal solution. There are intelligent ways to sample tighter as your solution is converging to put more of your samples in like the good space of the distribution. So if I was in this problem right here and my initial, like this was my initial normal distribution, like I'm wasting all these samples out here. So after I've done a few iterations, I should actually shrink it and I should make my new normal distribution like only this big. And now all my samples will be like in a useful set of the state space. So practical tip number one is like to look at annealing schemes on sampling-based models. The more important one, we talked about how all of these trajectory-based methods they're generating feed-forward controls U, not feedback controllers like optimal control does. And the problem is that if I optimize a trajectory and then I just go to roll out the feed-forward U, I accumulate error and I go unstable, right? The whole point of feedback, like why we do feedback control is because feed-forward control doesn't work. So the question is like, well, what are we doing? Everything that we just wrote down is only giving me a feed-forward controller. And the answer to that is, well, I use the feed-forward control for 1/10 of a second, and then I solve the problem again. So the way that we get feedback with these optimization-based methods is to solve them over and over and over, basically as fast as you possibly can. Receding horizon control. So receding horizon control is what happens when we take these trajectory optimization techniques and we try to generate feedback controllers from them, where we solve an optimal trajectory, we apply a tiny bit of it, but we accumulate some error, so we need to solve a new one because the original solution didn't tell you anything about what to do when you're like a tiny, tiny bit off to the left. The problem that we get when we start to go applying real-time when we go to start applying receding horizon control schemes is that these are nonlinear programs. These take time to solve, like potentially minutes. If we try to do trajectory optimization for like a full humanoid robot, to solve those NLPs to convergence takes like a minute, especially if I use an interior point method. That thing's going to have to crunch for 3 minutes, but I need a new control action at 100 hertz, right? Or like 50 hertz at least. So there's a question of like, how do I get fast feedback when my optimization problem just takes way too long to solve? And the solution that most people have landed on is note how all of these approaches are iterative, right? Like you don't solve the NLP in one shot, right? You do a convexification, you solve that QP. Then you do another convexification. The main thing that we're going to end up doing if we want to apply something like MPC is something called real-time iterations. And in real-time iterations, I'm going to do one step of whatever my iterative algorithm is, and then I'm going to get the new problem. So instead of solving the trajectory optimization problem to convergence, I'm going to take one step on it, and then I'm going to like apply that input, see what happens, and then start solving a new problem. I'm going to use my last solution as an initial guess. So the idea is that instead of solving one problem to convergence, I'm going to take one step on that problem, and then I'm going to start solving a new problem, and I'm going to converge to the optimal solution in time, like as the problem actually changes. And in fact, when people do MPC on like really fast systems that are hard to control for real, they won't even solve the QP to convergence, right? Like the sequential convexification, you create a quadratic program. Quadratic programs themselves are iterative to solve. Like you have to take steps on a QP to solve it. So like really aggressive real-time iteration solvers will take one step on the QP, throw the QP away, get a new one based on where your solution ended up, and then take one step on that QP, throw it away, and you do this as fast as possible. And if you do this, you can now get control at 200 hertz because we can take steps on QPs really fast. But your control is going to be like way lower fidelity, right? Because you're not even solving the QP to convergence. So there becomes this really big balance between like, how do we run the thing fast enough and solve the problem to high enough fidelity that we can get stability out of it. And there's the trade-off between solving to stability takes time and you don't have time because you need to recompute. So real-time iterations is definitely a thing to be aware of. And then the other thing that I wanted to mention with that is that real-time iterations requires this idea of a warm start, right? If I like throw away the previous solution, then I've made no progress. The whole reason that real-time iterations works is because my new problem is very similar to my old problem because my system has only evolved for 100th of a second. So the problem hasn't changed much, which means my old guess as to the solution is like still a really good guess for the next problem. Interior point methods do not jive well with warm starts because this barrier method sort of has this implicit like time in it. I need to relax the barrier through time. And so if you were trying to do it iteratively, you don't really know what to do with your barrier relaxation. Like when do you make the barrier more relaxed or less relaxed? This is very unclear. So pretty much all real-time iteration schemes are going to fall into this sequential convexification because the sequential convexification you can just spam, kind of like I was saying. Like you You literally will just update that QP as fast as you possibly can. You will take one step on the QP and then throw the actions out to the controller. And then I just want to note how far away what I just said was from where we started, right? We started with I can write down an optimal control problem that has like all of my system dynamics. It has an infinite horizon cost function, and the solution is a globally optimal feedback controller over the whole state space. But if we want to use this on a real system, I needed to take that, throw away the everywhere part, and just do trajectory optimization from where I am. Then I needed to throw away the continuous dynamics. I needed to make a bunch of approximations to transcribe it. I then needed to say, okay, I have to solve this thing approximately because it's a nonlinear program. And not only that, I'm not even going to solve it approximately. I'm going to take one step of an iterative method before throwing the whole problem away and getting a new one. So the real-time iteration scheme, which is the only thing that works on hardware, is a long way away from the principle of optimality. And there's like a big engineering jump that you need to sort of even relate those ideas in your head, even though they are, very related. That's optimal control. Yeah.
And how does this?
Great question. I plan to talk about reinforcement learning next week. And the reason I placed it like this is because reinforcement learning effectively seeks to solve the same problem, right? At least coming from my control plus learning background, I view these things as very much targeting the same class of problems. So the problem they're aimed at is the same. The solution methods could not be more different. RL, if we compare it to this like real-time iteration MPC scheme, what RL does is it sort of is going to combine a lot of the good things from here and it's going to amortize it so that we can run it fast. So RL is going to leverage offline compute. None of these methods can really leverage offline compute when you go to deploy it in real time, right? Like you need to see the state that you're in and compute from there. I can't prepare for that because I don't know what state I'm going to be in, right? So these methods, it's like you do all the tuning and setup beforehand, but no compute. And then you go online and you are computing like as fast as you possibly can on all your threads. Like your machine is burning up because you're doing as much CPU compute as possible. RL is going to flip the paradigm. It's going to light the GPU on fire for a month, but then when you get online, you have a small neural network that you just get to query, and that's like easy. Nothing hard about that. RL is not going to like spit out QP and feasible at you when your humanoid robot is like in the middle of a backflip. The RL is just going to kind of keep going. So RL trades all of this offline compute beforehand and a bunch of experience, really a bunch of sampling, to condense down a like simple policy that you then get to just query online. So targeted at a similar problem. There are some similarities, especially with the sampling-based solution approaches. But really, I would think about it in this like trade-off between online and offline compute. And then obviously, big differences in terms of modeling and these things as well. Obviously, RL doesn't like require a model that has gradients. It doesn't really require a model at all. You just need a simulator. So different requirements. But a good nod to next week. Yeah. So last week we were talking about simulators, and the main diagram that I was thinking of was this triangle between coverage, throughput, and fidelity. Okay, the digital twin one. This one, okay. The digital twin one was talking about, yeah, how you would have like a controller and that controller should expose an interface, and that interface should either go like directly to the real world or the interface should go to a simulator. And if you spend time like standing up those interfaces, then you can save some sim to real gap. This is all like on the inside of the controller. So yeah, if you were running a model predictive controller, then absolutely that would be using sort of a real-time iteration scheme in order to hit the rates you need for real-time control. And this is actually it's a good point. I think one of the reasons that digital twins are so important, or this idea of when you're doing simulation to really validate it like in the same way that you would validate the real one, is because something that you can fall into really easy is if you're taking an MPC controller, you can evaluate it asynchronously, meaning you take one step of your sim, and then you take as many steps on your MPC problem as you want, and then you take one more step on your sim. And this is like, doesn't help you realize sim to real transfer at all, because you can solve the NLP to convergence for, 2 seconds or 2 minutes every sim step. And so it's important to split those things apart, run the sim at real time, and then now you're forced to take these real-time iteration schemes, and you can actually see how the timing constraints are going to work out in a way that you wouldn't if you just stood up like kind of a standard asynchronous simulation pipeline. Yeah. So I think these sorts of timing constraints really motivate making that separation explicit. Any other questions? All right. Well, thanks for listening. Look at that. We keep going for 2 hours every single time. It's not my fault. I swear it's not.
We like it.
Well, thanks. I appreciate it.